Hello, everyone. Welcome again in Empowering Women Summit 2020. This is the 11th session, and we have more 9 sessions and 2 e-receptions and closing ceremony in 3 days. My name is Kardan Büyüktan Aktar, and I am the IEEE Turkey Women in Engineering Vice Chair. Today, we have a magnificent woman leader, Maria Alexandra Paun. Thank you for coming, Maria, today, being with us. I will read her brief bio right now. Maria Alexandra Paun is currently a telecommunications engineer at a Swiss Federal Office of Communication, working in access to markets and conformity of radio equipment, as well as being project leader in the field of drones. Dr. Maria Alexandra Paun received with honors her bachelor's and master's delivering in engineering diploma in 2008 from Politehnica University in Budapest, FILS, Romania, with a major in computer science, graduating top of her class. The master project was carried out at Swiss Federal Institute of Technology in Switzerland. During 2008 and 2009, she was awarded a postgraduate Marie Curie Research Fellowship at the University of Kent at Canterbury, UK, where she worked in the field of OCT between 2009 and 2013. She was assistant PhD student at EPFL. She received her PhD degree in June 2013 on the subject of Hall effect sensors. During 2013 and 2015, Maria Alexandra was visiting researcher at University of Cambridge, UK, with 2 postdoctoral fellowships from the Swiss National Foundation. Between 2016 and 2019, she was scientific researcher at EPFL, Switzerland, where she was focused on the development of electronics for medical devices. She has worked on various currently initial Switzerland-founded research projects with industrial partners in the fields of magnetic sensors and insulin injection pens, as well as being awarded by the Hassler Foundation 2 on grants to work on cochlear implants. She has published around 60 scientific papers, and her H-index is 10. She is an IEEE senior member. She is committed volunteering work within IEEE, as she is currently chair of IEEE Switzerland section chair, chair of IEEE Women in Engineering, affinity group in Switzerland, as well as member in IEEE Region 8 Women in Engineering Committee and member in the Region 8 Humanitarian Activities Community. This was the brief, not a brief, biography. Let me give the word to you. Today's topic is analysis of modeling medical devices. We hope to hear you. Let me open your...
Thank you. Please, yes, please open my presentation. Thank you very much, Kardan, for a very kind introduction. Just a small correction. I graduated from Bucharest, not Budapest, but it's fine. They resemble. It's fine. It's not a problem. It's a Polytechnic University of Bucharest.
Okay.
It's not a problem, but I really appreciate your kind introduction, and you really, let's say, opened up this discussion in a very nice way. Thank you very much.
Thank you. I'm now opening your screen right now.
Okay, yes, and if you could, yeah, it's excellent. Thank you very much, Kardan. Yes, so I'll let you know when to advance the slides, because I cannot share my screen from here, and you'll kindly helping me with this one. Okay, so hello to everyone. It is my great pleasure to be here on this occasion in such a powerful event, which by its name, Empowering Women, it's really saying a lot. So my talk today has already been mentioned, is called Analysis and Modeling of Medical Devices. And I shall be spending some time today in talking to you about my research topic that I had developed when I was performing research at the Swiss Federal Institute of Technology in Lausanne. Next slide, please. Okay, so I have imagined my presentation today in two different parts. I have two really nice talks, which one is about cochlear implants and the second one is about insulin pens. These two are two examples very much used worldwide today in treating various diseases. So these are two types of electronic devices, medical electronic devices. One is the cochlear implant and the other one is the insulin pen. I shall be giving you a general presentation of the cochlear implant. I shall be emphasizing the antenna modeling for a radio frequency identification cochlear implant with an emphasis on ANSYS HFSS modeling tool that I have used. And then I shall give you some simulations results while considering a multi-layered tissue model for the modeling of these type of implants. And then I'll give you conclusions and future perspective. In the second part of my talk, my intention is to guide you through some knowledge about insulin pens, the 3D dimensional model which I've performed in ANSYS Maxwell 3D. I'll give you some simulations results. I shall emphasize on the analytical model for the electrode capacitance, and I'll give you some numerical values of different parameters. By this, I shall be finishing with giving you conclusions and future perspectives. Next slide, please. Okay, part one, cochlear implants. Next, please. Okay, so as a summary of this first part, I shall give you a general description of what a cochlear implant is. I'll give you some design goals. I shall talk about what is novel in this research, because obviously cochlear implants have been around for some time, but what is really novel in this research that I have developed is the fact that for the very first time I have proposed the addition of temperature and humidity sensors to compensate any climatic changes of the cochlear implant. I'll really talk to you about in details about the antennas, both the radio frequency transmitter and radio frequency receiver in a cochlear implant, which have been carefully optimized and modeled in 3D. An analysis of a classical loop antenna will follow up, giving you precise dimensions of these antennas, and simulations results regarding the radiation pattern Smith chart's electrical field will be given at the end of this first part. Next slide, please. Next slide, please. Okay, thank you. So what is a cochlear implant? You all may know what it is, but I'll spend a few minutes explaining you about it. As you know, nowadays, there are approximately 360 million people in the world with a form of disabling hearing loss. It may be moderate, mild, or it may be permanent. Approximately 330,000 people have cochlear implants. It means that approximately 1 in 1,000 people wear a cochlear implant, while the other can use a form of hearing aid, which is only amplifying the signal. The main difference between the cochlear implant and the auditory, let's say, hearing aid is the fact that you need a cochlear implant when you have completely damaged auditory nerves. Let's say you have completely lost your auditory sense, and you need a cochlear implantation, which is a medical surgical procedure. While if you have some form of mild or moderate hearing loss, you only need a hearing aid, which is electrically amplifying the incoming signal to the desired level in order for you to hear it well. Okay, here in figure 1, which is placed in the left-hand side of the screen, you can see a diagram of the cochlear implantation. You can see that we basically have two antennas. One is outside, one is inside. One is the transmitter, and the other one is the receiver. In between those two antennas, a radio frequency link, meaning a wireless communication link, will appear, and it is via this link that will send all the signals. There are two magnets used to keep in place or to align the two antennas that we use in this radio frequency wireless transmission process. And obviously, in the outside of the ear, you have a speech processor, which is used to pick up the signal from the outside, which is actually a radio signal, and it really accounts for electromagnetical wave signal, which is being then transmitted wirelessly. And the most important thing is that it will arrive in the cochlea as an electrical signal, and it would stimulate it via an electrode array. But more on that later on. Of course, wireless communication reduces possible infections. It increases the patient comfort. It will actually be very much used by people having suffered a complete auditory loss, and is actually very, very important to do this cochlear implantation at a very young age, especially in babies. You will see later on why this is so important. Of course, we have here to master a few parameters because we are talking about a low-power ASIC design and implementation. We have to extend the battery life of the external unit. Obviously, there is no battery in the internal unit that would not be possible. And we obviously have to improve the radio frequency transmission efficiency in order to power, let's say, the signal and receive it at its maximum intensity. Just before going further, I would just like to point out that this is a surgical procedure when a patient is equipped with this cochlear implant. Actually, the surgeon is drilling a hole into the mastoid bone of the patient in order to insert the antennas. The link between the two antennas, and obviously it needs to insert the antenna on the inside of the skull. So this is done under general anesthesia, and it costs up to $60,000 just to have an idea about the costs. Next slide, please. Okay, I told you before that it's very important in babies to do such a cochlear implantation at a very young age, 1-2 years of age. Why is this so important? Because, as you know, in children, learning is based on speech recognition. So they learn by hearing, the parents and the other people talking, and then in this way they are learning. So if they cannot hear, they will not be able to perform speaking abilities, and they will become deaf mutes. The basic idea for this project was to compensate for any potential climatic changes that could affect our cochlear implant. Obviously, climatic changes such as temperature and humidity will affect the sound quality of the cochlear implant. You will see this later on, but this is really the novelty of this research that has been performed. And you obviously can see there are different types of people. For example, sportsmen, if they are using a cochlear implant and if it's affected by climatic changes, they can no longer perform their tasks. Next slide, please. Okay, so I've just told you that there are some environmental concerns about the quality of the sound in cochlear implants. For example, rain, transpiration, snow, or any kind of wind will affect the quality of the sound, incoming sound in the cochlear implant. Therefore, the signal that will arrive, demodulated into the brain of the patient, will be let's say, attenuated or affected by these climatic changes. Therefore, we want to compensate for any climatic changes. Next slide, please. Okay, how have we learned that these humidity and temperature changes affect the patients? We have really talked with them. So we had a total of 32 interviewees. There were approximately 50-50 female and male interviewees, and then they had different ages. And then they obviously had different professions. And approximately 42 people of the interviewees mentioned that signal interruption caused by humidity while wearing hearing aids or cochlear implants, it was a very problematic issue for them. Therefore, we noticed the need for compensating any potential humidity and temperature changes into the cochlear implant. And also we have noticed on this occasion the age of people with a certain type of hearing loss is getting down. So younger and younger people are having some kind of hearing loss issue. Next slide, please. Okay, how do we normally or traditionally do it? How do we normally compensate for this humidity? Let's say we do it either using hydrophobic capsules, absorbent chambers, different kind of patches, or we even use electric dehumidifiers that we are actually placing the hearing aid while it has been subject to some kind of climatic changes. We place it in an electric dehumidifier in order to, let's say, remove the moisture. Oh, this is not pleasant. Imagine, remove your hearing aid and place it there, or remove your cochlear implant. It's not even possible because you only have access to the external antenna just to compensate for humidity and temperature. So this is not possible, this is not pleasant, and it's very cumbersome for the patient. Next slide, please. Okay, so let's say here, if you want to learn more about this, I won't spend too much time on this because I really want to get you into the results, but I just want to tell you that, for example, as I already mentioned, you have an external and an internal unit in this cochlear implant. They are separated by skin and bone, and in between the external and the internal units, a radio frequency wireless transmission link is being created by the two antennas placed on opposite sides. Therefore, the signal can be transmitted. Obviously, the signal, the sound signal, is an electromagnetic wave that is being transmitted via this radio frequency link. But we must use a digital signal processing block in order to convert the sound into bits and send it over the radio frequency link. Once it gets into the internal unit, when the stimulator is charged, it decodes the radio frequency bit information and converts it into electric currents for the electrodes. For this array of electrodes, which is situated in the cochlea, as I mentioned before, it must be stimulated. Therefore, we bypass the damaged auditory path and the auditory nerve, which is no longer functioning properly. We are talking about a complete hearing loss. And in order to bypass that, we send the signal as electrical stimulation into the cochlea. Next slide, please. Okay, so we have imagined a multi-layer tissue model here with an emphasis on actually on two-layer tissue model, where we have imagined the two antennas, both the external and the internal antennas, separated by skin, bone, and brain, if you want to take into account the third layer. We have noticed that two layers suffice for our analysis. Here in table number 1, you can find the main parameters such as conductivity and relative permittivity of the tissues, which are parameters necessary for the 3D numerical analysis that we are developing further on. Next slide, please. Okay, if you want to learn more about the physics behind it, obviously, once the sound wave is beginning to traveling via different media, these are lossy media. Therefore, the signal is being attenuated by the tissues. The wave propagation is obtained as an attenuation of the incoming signal while traveling through different media. We have an attenuation by an exponential factor. Therefore, the intensity of the signal, for example, is decreasing with the distance by a factor which is called the attenuation factor. The attenuation factor, the attenuation constant, is different for the skin and the bone. Next slide, please. Okay, we have looked into a very precise three-dimensional model of the antennas, and we have done it using ANSYS HFSS tool. This has been a tool which has allowed us for powerful 3D physical simulations while giving precise dimensions for the antenna and while being able to introduce all the tissue parameters in order to faithfully replicate the real media which are found inside the human body, here with an emphasis on the human skull. More precisely, we have modeled two tissues, skin and bone, separating the two antennas. Inside the skull, we obviously have the receiver antenna, which is in this case a loop antenna with precise dimensions that you can see them on the screen. We have used a remote powering and data transmission frequency of 2.45 gigahertz, which is a very well-known frequency in the ISM band. Next slide, please. Okay, so the simulation results pointed us to values of the Smith charts, which are very much necessary for this type of analysis, because Smith charts, as you all know, are useful for any kind of radio frequency designers, and they show various parameters such as the reflection coefficients, scattering coefficients, admittances, impedances, etc., including also noise. You can see here in figures number 8 and 9, you can see the Smith charts for S11 and S22 symmetrical coefficients, whereas in figure 9 you can see the Smith chart for S12 and S21. They are grouped 2 by 2 because they are placed in a symmetrical matrix. We have performed a frequency sweep from 1 to 3 gigahertz with a step of 0.01 gigahertz. It is worthwhile mentioning that for this particular simulations, the results that you are seeing on this screen, the antenna was first placed in air. So there was no other tissues, just the air. We have done this obviously for the external antenna, which is only being placed in air, while for the inside antenna, which is a receiver antenna, it will be placed into a two-layer tissue model, including skin and bone, as you will see later on. Next slide, please. Okay, here you can see the Smith charts for the same frequency sweep as before from 1 to 3 gigahertz, but this time the antenna is placed, as I mentioned before, in the two-layer tissue model containing skin, bone, obviously no longer is in air. And it's worth mentioning that the tissue parameters are all taken for table number 1, which I showed you on previous slide. You can take a look at the values. You can obviously see that the Smith charts, the scattering factors are much more prevalent inside the tissues. So the wave is scattering more in the tissue than it was scattering in the air, which is obvious. Next slide, please. Okay, if you want to look into more details about the electric field simulation, you can see here in figure number 12, the electric field for the design loop antenna. You can see that we have placed it first in air, and the results are in the left-hand side, while we have also placed it in the multi-tissue model in the right-hand side. Here, it's really worthwhile mentioning that we have, for example, you obviously see that we have a decrease, an important decrease of approximately 87% in the electric field, while going from air to multi-tissue model, which is obvious. This is due to the attenuation of the waveform while traveling to different lossy media. And you have to also take into account the fact that this is a very precise three-dimensional physical simulations, because the initial model of this cochlear implant takes into account not only the antennas, but it also takes into account very precisely the tissues. And these tissues are characterized not only by their parameters, which I showed you before in the table number 1, but they are also characterized by specific depths. For example, for the skull bone, the depth was 7 millimeters, and for the skin, the depth was approximately 12 millimeters. So these are important factors to take into account when modeling in order to have a precise, let's say, analysis. Next, please. Okay, here one can see the radiated electric field. Obviously, you can see in a color-coded map. Obviously, the red points are the hottest points. It means they have the highest radiated electric field. You can see it on the outside where it's more red, and then it drops to, let's say, cooler colors. It gets to the blue, which is actually the lowest value of the radiated electric field. If you are interested, you can take a look at the values. You can have both. You can have a look at both a 3D polar representation, which is located in figure number 13, or you can take a look at figure 14, which is actually giving you the total radiated electrical rectangular contour plot. This is obviously in 2D. Next slide, please. Okay, of course, what would it be an antenna analysis without the analysis of the return loss? Obviously, we had to look into the return loss of the antenna, and then here you can see in figure number 15 the return loss in dBs for the antenna placed in air. Again, there was a frequency sweep from 1 to 3 gigahertz. And you can see that the resonance frequency is around 2.7 gigahertz for the antenna placed in air. Obviously, we would like to approximately resonate at 2.45 gigahertz. So for the antennas located inside of the skull, further tuning of the antennas have been performed. Next slide, please. Okay, again, radiation pattern. Obviously, the antennas radiate, so we are very much interested in looking how much they radiate. So here you have some radiation pattern and some total field at 2.4 gigahertz. This is plotted against theta angle, and this theta angle takes values from 0 to 180 degrees. And obviously, there are multiple curves represented on each figure for different value of phi angle from minus 180 to 180 degrees in steps of 2 degrees. Next slide, please. Okay, so this leads me to the end of the first part. This work was focused on presenting a loop antenna, which is using cochlear implants with very precise, carefully chosen dimensions. The antenna was characterized through a three-dimensional physical model. Smith charts for the antenna placed in air have been obtained, as well as for antennas placed in by tissue models. The representation of the electric field versus the theta angle, as well as the radiation pattern of the antenna in skin, were also included. As future research directions, we can mention the fabrication of the antenna and its subsequent testing. Next slide, please. So these are a few references that you can look into. These are papers that I have published while doing this particular type of research in EPFL, Switzerland. Next slide, please. Okay, these are some acknowledgements. This has been funded by Hasler Foundation from Switzerland. And next slide, please. Okay, this gets me now into the second part of my talk. I really wanted to give you a flavor of two different types of medical electronic devices. I could have only emphasized one, but I really wanted to give you a flavor of both of them. At the very beginning, I told you that I have been tasked with looking into the analysis and modeling of medical electronic devices. But one could ask the question, but is the insulin pen, okay, an electronic device? To my knowledge, is it not only mechanical? And one would say yes. The insulin pen, in its, let's say, most common form, it's purely mechanical medical device. But in my particular project, we have transformed it into an electronic device by placing smart electronics around it. You will see later on. Next slide, please. Okay, we have looked into a three-dimensional physical model for the capacitive measurement in an insulin pen used by diabetic persons. We have used ANSYS Maxwell 3D software this time in order to faithfully model an insulin pen and to numerically assess the electron capacitance. You'll see more later on about what the electrode capacitance is and what is it actually being used for. We have used a multi-electrode configuration of 3, 4, 6, and 8 different electrodes of given dimensions. All of these configurations have been considered for the smart cap, which has been added to, let's say, regular mechanical pen. And you could also get some capacitance values between face-to-face electrodes obtained in different biasing conditions. Next slide, please. Okay, just a little bit of overview about what diabetes is. Of course, we all know what diabetes is and also what insulin pens are. We know that diabetes nowadays, it's actually the 10th most common diseases in patients and is also the 6th most deadly disease in patients. It's actually an endocrine disease which causes high sugar blood levels, and it's actually a metabolic disease. It can be of type 1 when the pancreas does not produce enough insulin. This only affects approximately 10% of people. This is actually caused by the loss of beta cells, and it's an autoimmune response of the body. Or we can have type 2 diabetes, which is the most common one. It's affecting actually 90% of patients. And in this case, insulin, it is produced in some way, but it's not properly used throughout the body. In 2014, 422 million people were affected by diabetes. But a few years later, I have here another statistic, in 2019, approximately 463 million people were affected by diabetes. So one can see that in 5 years' time, you have an increase of 10%. So this is going, unfortunately, up, and we have more and more people affected by diabetes. Obviously, in order to treat this disease, we have two possibilities. You can have, obviously, you can have some drug that you can take. You can have some metformin that one must take. This metformin is actually used in type 2 diabetes. It's taken orally. And this is actually to regulate the level of the sugar in your blood. Or one must inject insulin if we are talking about type 1 diabetes. So we really have to supplement the body by administering an injectable solution of insulin in a subcutaneous or intravenous way. And this type of insulin is administered in this way by an insulin pen, which is a very modern way of giving injection of insulin into your body, because one maybe can remember that in the past there have been very difficult and cumbersome ways of giving patients insulin, like pumps, which were very heavy and bulky to to use. So here you can have, let's say in figure number 1, you see a glucometer, which is used to monitor the amount of sugar in your blood. This is very much used to know the amount of sugar that you have, and of course then to treat orally by taking some kind of metformin based drug. This works very easily. You just inject, you just make a little drop. You take a little drop of your blood, and then you place it onto a strip, and this is being fed into this kind of small device which reads the values. And obviously, if you have diabetes, you would have approximately more than 200 milligrams per deciliter of insulin. So that would be an abnormal level. So you would already be diabetic with more than 200 milligrams per deciliter of sugar in your blood. Okay, in figure number 2, this is really what actually is concerning us. One would use an insulin pen to inject himself or herself with insulin. Here you see a quick pen, Humalog quick pen, which has been also used in our research project. Here it's a basic mechanical only insulin pen, which is used to inject insulin into your body. And you can see here that you twist it and you inject yourself with a certain dose of this insulin. It can be, in this case, probably an insulin Lispro. And just to give you an idea about the costs, approximately 5 of these pre-filled pens, which each contain a 3 milliliter injectable solution of insulin, cost approximately $550. So 5 of these pens would cost approximately 550, so a little bit more than $100 per each pen. So this is actually used a lot now. Only in 2016, approximately 8 people were using these insulin injection pens in the European Union, and this is very good because these are actually disposable pens, and then you can throw them away, and they are preferred to their refillable counterparts. The next slide, please. Okay, we have looked very carefully and very precisely into this. We have developed a 3-dimensional physical model of a customized, improved, highly optimized insulin pen. Why is it improved? Because now it has become, as I mentioned before, an medical electronic devices. We have started off with a regular pen, which is mechanical only pen, and we have added on top of this a smart cap, which is equipped with electrodes. These electrodes, this is actually part of a patent that was made with this research project. We have added a number of electrodes in order to be able to calculate precisely the capacitance, because there is a direct relation between the capacitance and the volume of insulin that you are injecting into your body. Therefore, you have a more precise definition or measurement of how much insulin you are injecting into your body. Therefore, this pen is marked in the sense that one can track the exact amount of insulin injected into one's body, and also it can then feed this data to a base station via a wireless Bluetooth connection that we had also developed during this project. So this was a novel idea. This is now being sold and manufactured by our industrial partner that we have developed our project together with. So here you have all the dimensions. You can look by yourself, all the dimensions of the pen itself. You can see the dimensions of the electrodes in the cross-section, etc. Next slide, please. Okay, we have looked into 3, 4, 6, and 8 different type of electrodes. This number was varied in order to see which is the best configuration. Obviously, you can see here that we have looked into various levels of insulin. So, for example, we have a pen full of insulin, and then we have slowly started to inject and to release insulin. Therefore, we were able to calculate via three-dimensional simulations the exact amount of the capacitance. Next slide, please. Okay, if you want to have a look on this particular slide, you can get all the dimensions of the cap, and you can get all the dimensions of the different layers into the cross-section of this type of insulin pen. And these dimensions have been used into the three-dimensional physical model. You can obviously see here all the layers in a cross-section between two electrodes, which are here signaled in red. And next slide, please. Okay, because we are talking about different layers into this insulin pen, obviously you can imagine that you have this cap, which is, for example, in plastic, but then you have the insulin reservoir, so the insulin ampoule, as we call it, which is in glass, and then obviously you have some other bits and pieces of glass, of air, of plastic, etc. So all these different layers have been included into a model, and we could get the equivalent capacitance circuit model for this situation. You can have a look at here. It's a very nice equivalent capacitance, which is actually very simple, but it's very useful in this situation for us to get the idea of how much capacitance we have into the pen. Next slide, please. Okay, more details about everything that you want to know: thickness of the electrodes, lengths, different dimensions, different electrode interdistances, thicknesses of all the layers, all the electric permittivity of media are all in these three tables. I can let you look into these, and you have them all here. That is very important in order to have an accurate 3D model. Next slide, please. Okay, so we have developed a very precise analytical model. I will not spend too much time on this because there are basically equations and integrations. So next slide, please. Obviously, you know the capacitance is epsilon times A divided by the distance. So these are simple, basic calculations of the capacitance. But as I mentioned before, even though they are simple, they are very quite useful for our case, for our situation. Next slide, please. Okay, obviously here the modeling of the insulin pen would not be complete without the modeling of the insulin ampoule. So while you start releasing or injecting some insulin, you will have a portion of air and insulin inside the insulin reservoir. So these via the K1 and K2 ratios account for a precise, let's say, and faithful reproduction into the three-dimensional physical model, because this is analytical modeling. So analytical modeling together with the 3D physical model give you a full overview of what this insulin pen can do and what the values of the electrode capacitances are. Next slide, please. Okay, just to point you out that although we have talked up until now about basic capacitances, which are straightforward and are learned in secondary school of physics. Here, the most important thing was that we don't have a parallel plate capacitor, and we have this type of shape, like, you know, of a part of a cylinder type of plate capacitor. And we had to perform some averaging via an integral, via the average value of a function, in order to be able to apply the classical electrode capacitance formula while transitioning from cylinder plate capacitor to parallel plate capacitor. Next slide, please. Okay, more into this if you are interested. I wouldn't spend too much time, but you have here all the integration details. Next slide, please. Okay, again, more details if you are interested. This has been also published. Next slide, please. Okay, here we finally get to the formula which is being used. This takes into account all the distances, all the thicknesses of various layers, as well as the electrical permittivity one can use this in full confidence. One can use this electric capacitance definition for our particular insulin pen. Next slide, please. Okay, here getting now towards the end of the presentation into the results and discussion sections. We have used actually here into this results section, we have looked into 4 electrode cap configuration, and you can see in figure 14, 15, and 16, you can see here various values of the capacitance variation with respect to the K1. So this would be insulin ratio, and you can obviously that the capacitance is decreasing, which is normal. If you start injecting insulin into your body, you will get more air and the capacitance is dropping. And here you have also various polarization schemes. You have also not only 2 versus 2 electrodes, but you also have 1 versus 2 electrodes biasing situations. Obviously, why are we doing all these 2 by 2 or 1 by 3? Why are we doing various simulations, and why are we looking actually into various numbers of electrodes? Why don't we just have 2 electrodes and that's it? Why do we use 4 or 8 or 6 or 3? The fact is that this is the basic idea here, is like a current spinning technique. So you turn your device, and each time you polarize it in a way and you measure in a different way. And all this time you are averaging it and adding it phase by phase. And in the end, what you get is actually a value which is less subject to variation, because it has been already averaged on 4 phases. So it's like actually a method which is used for compensating the offset. And it has also been used by me in my PhD thesis about Hall effect sensor, compensating the offset by using the current spinning technique and using various phases of biasing and of measuring the device. You can have a look at all the values here. We have been actually in the range of 7 to 8 picofarads, which is very low value. Obviously, it's in the range of picofarad, but we were also able to see that obviously 2 by 2 brings a higher capacitance value, but also we can see that when the distance is like in figure 16, when the distance between electrodes is beginning to drop, obviously the capacitance will be less. So here you have some values, you can have a look at them, and this has also been published. Next slide, please. Okay, more results here about 3, 4, 6, and 8 electrodes. One can have a look to see that the electrode capacitance for different insulin injection cases in 4 electrode cap configuration has given us particular numerical values in the range of a few picofarads. And you can also see for different injection ratios of insulin. And obviously, we have been interested to see how much do we gain in capacitance for each biasing case. So you can see that we gain approximately 50% in capacitance for the first biasing case. And the curves have been fitted in this case with linear regression. The desired linear behavior of the injection has been proven in this case because we were really interested to have a linear response of our sensor in this case. Next slide, please. Okay, I would like now to give the conclusions to the second part. We have been interested in this second part to do a complete both analytical and 3D models for an insulin pen. This has been developed using ANSYS software. And the novel idea here is that we have equipped a mechanical insulin pen with a smart cap. And we have developed in this smart cap, smart electronics, smart ASICs, in order to be able to precisely measure the capacitance. And this would give us a precise value of the dose of insulin that one injects. The variation of the sense capacitance for different insulin injection scenarios, biasing schemes, and inter-electrode distances have all been given to you numerically. And we have proven on this occasion the linear behavior of the injection. We have obtained a sense capacitance in the order of a few picofarads with 2 by 2 capacitance at approximately 7.8 picofarad and 1 by 3 capacitance, obviously less than that, at approximately 6.8 picofarad. This has all been for a 100% insulin pen case scenario. Electrical measurements for the electron capacitance have been obtained, and some of them have been published, some of them are under publication. Next slide, please. Okay, a few references of the papers that have been published. Some of them are also under preparation at the moment. If you are interested to see about that, please have a look. I have more. If you are interested, I can share with you more publications that I have authored. Next slide, please. Okay, I would like to thank for this particular second part of my research to CTI, which was the Commission for Technology and Innovation here in Switzerland, which has awarded us a Smart Cap data recorder for insulin injection pens grant to perform research. Next slide, please. That's all. Thank you very much for your kind attention. I hope I didn't talk too much. I hope that this was interesting to you. And if we still have the time, and I hope we still have the time, I'll be more than happy to take on some questions from the audience. Thank you so much.
Thank you very much as well. It was very educative and interesting for me presentation.
Thank you very much.
Thank you for being here, and thank you for researching that areas. Thanks for me. We don't have any questions in the comments part, but I have one little questions.
Sure.
In the external ear implants, there somebody cannot be proper for that implants. In the cochlear implants, is the range changed? And maybe the not suited ones can be used cochlear implants as well.
So if I understood correctly your question, so for example, already the external part of the cochlear implant can be associated in a way with a hearing aid, because it picks up the signal from the outside and it looks a little bit like a hearing aid. It just has a microphone and a little amplifier, and then it sends it through. Obviously, the main difference is that you have to use the cochlear implant if you are deaf. So if you have no longer any kind of hearing, you can no longer, like for example, the auditory nerve is completely damaged. The signal which is coming from the inside cannot be amplified anymore because the auditory path, the auditory nerve is damaged. So you cannot do anything. Whereas cochlear implants are used, okay, for deaf people or people having suffered the complete hearing loss. You can have various levels of hearing loss, and they can be easily compensated by hearing aids, which are very little, are non-invasive. You don't need, obviously, a surgical procedure, and they only amplify the signal to a certain level. And this, for example, in terms of the price, also hearing aids can range from $1,000 to 6,000 euros US dollars, depending on the technology inside. And I would say that the choice in the cochlear implant or the hearing aid is purely based on the degree of your hearing loss. If this was your question, I hope I answered. If not, please. Okay.
Yeah, that was. Because our elder people are mostly using that aids and
exactly.
not coherent ones. So I'm
exactly.
just saying.
Exactly, absolutely. So even as I said, most of the people are using, so only 1 in 1,000 people is using the cochlear implant. The others are using a certain type of pure amplification of the signal in the form of a little hearing aid.
This was my question, and our time is done. We have another session right now. Thank you for being here with us. Thank you. Today we were here with a magnificent woman, Maria Alexandra Paun. She was with us. Thank you, and right now.
Thank you so much, Carden. You have been a wonderful host as well. It was my pleasure to be here. I hope this was very, let's say, informative for you and useful, because, you know, nowadays in this type of age and time of era, medical devices are very important for humankind. So I hope I shed some light on some important aspects. Thank you so much, and see you next time.
Bye. Thank you.
Bye-bye. Good evening.